Hello, grade 12s. Welcome to our physical sciences session. Today, our focus will be on electrochemical cells, but we are going to put our main focus on a galvanic cell. Okay. This is a topic that was done last year in grade 11, whereby most of the definitions were explained at that point. In grade 11, we were looking at mostly the definitions, whereby we looked at the definitions of a galvanic cell, definition of an electrolytic cell, the definition of oxidation and reduction in terms of electron transfer, and the definition of oxidation and reduction in terms of oxidation numbers. So I'm not going to explain too much in terms of what are those definitions for this year because we have done them last year in grade 11. We also defined an oxidizing agent and a reducing agent in terms of oxidation and reduction. We also defined an anode and a cathode in terms of oxidation and reduction. We defined an electrolyte, and we also defined electrolysis. Other objectives of the lesson that we are also going to focus on, we are going to give and explain the relationship between current in an electrolytic cell and the rate of reaction. Remember, these are reactions, and it is very important to understand the relationship of what is going to be produced or what is going to be used in terms of the rate of reaction. We are going to state that the potential difference of a galvanic cell is related to the extent to which the spontaneous cell reaction has reached equilibrium. In the previous lesson, we have already known what do we mean by chemical equilibrium. So chemical equilibrium is also going to be part of this lesson because we are going to deal with reactions, and we are going to deal with reactions that are occurring at the same at the simultaneous rate. We are going to describe the movement of ions in the solution. We are going to state the direction of electrons flow in the external circuit, write down the half reactions that occur at the electrodes, and state the function of the salt bridge. The other objective of the lesson, we are going to predict the half cell in which the oxidation will take place when two half cells are connected. This is very important because when you say we need to predict, you need to know exactly where will the reduction and the oxidation reaction will occur. We are also going to write down the overall cell reaction by combining the two half cells, and we are also going to use the table of reduction potential, which was also used last year in grade 11, to calculate the EMF of standard galvanic cell and use the positive value of a standard EMF as an indication that the reaction is spontaneous under standard condition. The pre-knowledge. All the definitions that I've mentioned, they were the pre-knowledge that we did last year in grade 11. However, the pre-knowledge that you must know before you start this lesson, you must know what do you mean by oxidation numbers. You must be able to calculate the oxidation numbers, and you must also be able to assign oxidation numbers of different molecules and compounds. Then, you must also be able to define redox reaction. Redox is an acronym. Acronym meaning that this is an abbreviation of two words, redox. By redox, we mean reduction, oxidation, reaction. So redox is an acronym. Now, redox reaction involves the electron transfer. The word electron transfer, it means the electrons will be lost and gained by the substances that are going to undergo the reactions. Therefore, most of the time, there is this misconception of transfer meaning to lose or to release only. But transfer means going and coming of those electrons. Then you are going to describe the redox reaction, whereby we are going to look at what happens to the oxidation numbers, because the only way to say redox reaction has occurred is when you also look at the oxidation numbers changing. If the oxidation number of a substance doesn't change, it means that specific substance didn't undergo redox reaction. So as in grade 11, you have dealt so much with oxidation numbers, it's going to be easy for this here to just assign the oxidation number and see whether the oxidation numbers can change in order for you to say the redox reaction has taken place. Now, these are the definitions of oxidation and reduction in terms of oxidation numbers and also in terms of electron transfer. Oxidation is a loss of electrons, meaning that when the reaction is oxidation, it means the electrons will be lost in that reaction, will go away from that substance that is undergoing the loss of electron. And what will happen to the oxidation number? The oxidation number will now increase. So if you see an oxidation number increasing, it means that reaction or that substance has undergone oxidation reaction. Now, reduction reaction is the gain of electrons, or is when the oxidation number decreases. We are going to look at what do we mean by oxidation number increasing, what do we mean by oxidation number decreasing. Then we have the agents. We have a reducing agent and an oxidizing agent. What are these agents? They are processes. Oxidation reaction, reduction reaction are processes. Those processes are being undergone by the agents. So the agent that loses electrons is referred to as a reducing agent. Then you ask yourself, when will the electrons be lost? The electrons will be lost during the oxidation reaction. So a substance that is losing the electrons is referred to as a reducing agent. And that agent is found under the which process? Under oxidation reaction. And what will happen to the oxidation number of that agent? It means the oxidation number of that agent will increase. And if the oxidation number of the agent, which is a reducing agent in this case, is increased, then we say at the end that agent is being oxidized. Now, it can be confusing a little bit because we are saying it's a reducing agent, but at the end of the day, it's being oxidized. By being oxidized, we mean its oxidation number has been increased. Now, the next agent is the oxidizing agent, which is a substance that is being reduced. So when the oxidation number of that agent is decreased, it means that agent has undergone reduction reaction. Reduction reaction means there are some gain of electrons. But remember, because this reaction is a redox reaction, it means you cannot wait for a substance to lose and then after some time a certain substance gain. No, the losing and the gaining occurs simultaneously, meaning that immediately when a reducing agent loses an electron, it is immediately being gained by the oxidizing agent. So because why? Electrons are charges. We know that according to the law of charges, charges cannot be lost or gained, but it means they can be transferred, meaning that you cannot say, I have lost the charges. I don't know what happens to this charge. I don't know where did it go. It means you must be able to account for it. So immediately when you say, I'm losing a specific charge, something must gain it immediately because it cannot be lost without being gained. And what makes it to be lost is that process, that substance that will make you to lose so that it can gain. So that is why when you're coming to the agents are the ones that are making the process to be possible. The process is going to be possible whereby if there is an oxidizing agent, there must be a reducing agent that will automatically gain that electron from the reducing agent. Therefore, it is very important to understand that a reducing agent is the one that will be able to lose electrons. But now it is very important to know why and how can that substance lose electrons and how does that substance gain electrons. According to the periodic table, we know the periodic table is always part of our chemistry. And understanding the periodic table will also make you to understand why are these agents losing and other agents gaining electrons. Because when you look at the periodic table, from the explanation of the periodic table, if you have a periodic table in front of you, you know we have metals and non-metals in the periodic table. And we know that what are the properties of metals? What are the properties of non-metals? Even the transition metals, we know that they are metals. They can also have that ability to lose electrons. So you must understand why are you saying you have lost and what makes you to lose, what makes you to gain electrons. Now, we have two types of electrochemical cells. Even though today we are going to look at only galvanic cell, but it is very important to know the distinction between a galvanic cell and the electrolytic cell. Galvanic cell is the electrochemical cell that converts chemical energy to electrical energy, meaning that for you to have, for a galvanic cell to exist, it means you must firstly have chemical energy as part of your reactants so that you can produce electrical energy. And galvanic cells are spontaneous, they undergo spontaneous reaction. They occur spontaneously on their own. The other cell is an electrolytic cell. An electrolytic cell is a cell that converts electrical energy to chemical energy, meaning that for you to have an electrolytic cell, you must firstly have electrical energy, which will be converted to chemical energy. So when you look at the two cells, you can see that the distinction is not so much. So you must be very careful of which produces what. And what is it that you must have as a reactant, and what is it that you must have as a product. So if you want electricity, if you want to produce electricity, which is electrical energy, it means you must have an electrolytic cell. However, if you want to produce chemicals, it means you must use a galvanic cell, because the product of the galvanic cell are the chemicals, but the product of the electrolytic cell is the electric energy. So in terms of electrolytic cell needs energy to occur. So it's not spontaneous as a galvanic cell, but it is non-spontaneous. Now, Redox, as I said, is an acronym and is meaning the electric transfer. I also emphasize the issue of metals that will be used also, because the property of metals, one of the property of metals is that they can, or they are able to transfer electrons. So that is why they are mostly used as electrodes. Electrodes are the substances that can be able to conduct electricity in a form of a metal. So when you look at the definitions, the two definitions that I explained, they are also sometimes confusing to some of the learners. So sometimes we use some of the abbreviations as tips. This is not just a one recipe that you can be able to use in order to remember these definitions. But you can use the Leo-Gay definition to be able to distinguish between the oxidation reaction and the reduction reaction, whereby Leo means loss of electrons is oxidation and gain of electrons is reduction. So it's lion grr, like the lion grr, which is the sound. So Leo Gay is one of the ways that we can use to be able to distinguish between oxidation and reduction, because the distinction is too little, or they are closely related to each other. You cannot even notice which one loses and which one gain. So that is why it is very important to be able to distinguish. But the main thing that you must understand that these reactions, they occur simultaneously. Immediately when the oxidation reaction occurs, reduction must also occur at the same time, because there's no one that will occur without the other one occurring. Now, I also explained in terms of the oxidation, the increase of oxidation number, and reduction, the decrease of oxidation numbers. Now, okay, this one was also explained. Now, let's look at the words, because these wording are the ones that are making us sometimes to get confusion in terms of, we have what we call an electrode. As I explained, an electrode is an electrical conductor. Understanding the different substances, matter and material, you know that metals mostly are used to conduct electricity. So most of the electrodes that we are going to use in our examples are the metals, are the electrodes that are metals that will be able to transfer electricity. Because remember, redox reaction is about electron transfer, and electrons can only be transferred through a metal. The electrons cannot be transferred without being conducted by a metal. So that is why we are using these electrodes as the path of the electrons to be transferred from one substance to the other substance. Now, we have these electrodes, and these electrodes are also named, or they are also classified. The electrode that will be undergoing oxidation reaction will be referred to as an anode, and the electrode that will be undergoing reduction reaction will be referred as a cathode. So we can also use these types of oxen and red cat. Oxen means oxidation reaction, we get an anode. Red cat means reduction reaction, we get a cathode. So red cat for reduction that will undergone by a cathode, and ox by anode. So these are some of the tips that we can also use to distinguish between the two electrodes, because it is very important to know which electrode undergo what type of reaction. Then from the electrode, we have an electrolyte. The first one was an electrode. The electrode is in a solid form because it's in a metal state and it needs to transfer electrons. But in terms of the electrolyte, electrolyte is an aqueous solution that will be able to also conduct electricity. So the distinction between an electrode and electrolyte is very important to be understood, because as you look at the electrode, we talked about the metal solid that can transfer electrons. But here we talk about an electrolyte which can also be able to transfer ions in a solution. So it is very important to understand what is an electrolyte and what is an electrode. So it's a solution that can be able to conduct electricity, and we refer to it as an electrolyte. And then we have a process that is known as electrolysis. So the way I've put the words is so that you can be able to say what is an electrode, what is an electrolyte, and also go to the process of electrolysis to know what exactly electrolysis is. Electrolysis is the chemical process in which electrical energy is converted to chemical energy. By looking at electrolysis, you can easily refer to it because electrical energy will be converted to chemical energy. So you can see that electrolysis process is closely or is directly connected to the process of electrolytic cell, whereby we have used electrical energy to get chemical energy. The use of electrical energy to produce the chemical change. This is another definition that you can use to explain what we mean by electrolysis. Now, let's put our concentration of a galvanic cell, because in a galvanic cell, the galvanic cell is what we are going to do for our lesson. In a galvanic cell consists of two half cells separated by a salt bridge. I normally hear people saying a galvanic cell is when you have two beakers. It's a cell where there are two beakers. This is not about the two beakers, but it's about the two electrolytes. And it's also about those two electrolytes being separated by a salt bridge. So it is very important. Sometimes you are not going to get any beaker. You can get a YouTube where there are two electrolytes. You cannot say, now this is no longer a galvanic cell because there are no two beakers. The lesson is not about the beakers, but the lesson is about the two electrolytes separated by a salt bridge. Now, there are electrolytes which have the same ions as the metals used in a car. This is very important. The electrolytes and the electrode must communicate with one another. If you have an electrolyte and you have an electrode, as we are going to look at the examples that are going to follow in the next slides, you will see that they are saying those electrolytes must have the same ions as the electrode. Remember, an electrode, in our case, we have used metals. And as the metal, it means like if you have a specific name of an electrode, you must have the same electrolyte of the same ions of that electrode. Meaning that if you have a zinc as your electrode, the electrolyte of zinc must have the zinc ions. So you will think about any electrolyte that can have zinc ions, like zinc nitrate, zinc sulfate, which will always be able to connect or to communicate with the electrode. The electrodes are connected in a galvanometer or a voltmeter via the external circuit. We will look at the example of a galvanic cell, and we will explain what do we mean by the external circuit and also what do we mean by the internal circuit. So they are saying they are connected by that galvanometer, which is used to detect even a smallest amount of current. A voltmeter sometimes it is not user-friendly in terms of a galvanic cell, because if the current is too little, a voltmeter sometimes cannot even detect that amount of the current. But a galvanometer is so much accurate to detect even a little amount of current that is flowing. And then we also have the salt bridge, consists of a salt which allows the movement of ions between two half cells. So it is very important to choose the suitable salt bridge for your specific cell, because some of the salt bridge are not soluble enough so that they can allow the movement of ions. So the salt bridge is also going to be part of the galvanic cell. So for you to be able to identify a galvanic cell, it means it must have a salt bridge, it means it must have two half cells, and it means also it must be connected by a galvanometer or a voltmeter. Now, we are going to use let's look at the zinc copper half cell. I think by now we know that zinc and copper are two transition metals that we find in the periodic table. The other one is element number 29 and the other one is element number 30. They are neighbors. Now, if you look at this cell, you can see that on this cell we have two electrolytes. The first electrolyte is zinc sulfate and the other one is copper sulfate. And then on that zinc half cell, you can see that the zinc electrode, which is a metal, is inside or is immersed inside the zinc sulfate electrolyte. This is what we were talking about in the previous slide, to say the ions in that electrolyte must be the same as the ions in that specific electrode. And also under the copper half cell, you can see that we have copper sulfate, so it means we have copper ions inside the copper sulfate. This will take you back to grade 10, whereby you must remember that when you have a compound, which ions are responsible for that compound. For example, if we have zinc sulfate, you must be able to say which ions are responsible for zinc sulfate. They are zinc 2+ ions plus sulfate ions. Therefore, it is very important to know which ions are responsible for a specific compound. Because these ions, we also go further in grade 10 and say they are classified as cation ions and anions, whereby the positive ions are referred to as cation ions, and this one are referred to as, the negative one are referred to as anions. So you must be able to say, if we have cation ions and anions, if this is a balanced zinc compound, the number of positive ions and the number of negative ions must be the same, because for it to be neutral, it must have the same number of positive and the same number of negatives. Also, when coming to copper sulfate is having copper 2+ ions plus sulfate ions. So from this information, you can see now that that is why the copper is inside the copper sulfate solution or electrolyte, because of these copper ions, which are the ions of copper, and also the zinc ions. Now, we also have what we call a salt bridge. A salt bridge, remember, is the one that we said it also symbolizes that our cell is a galvanic cell. And it is also going to have its own function in this specific cell, because it is here for a purpose. We must know why is a salt bridge important for a galvanic cell. And we must also have a wire. A wire, this can be a copper wire. This can be any wire that can be able to transfer electricity, because remember, during this galvanic cell, what is going to be formed is we are going to form electrons. We are going to form electricity. So electrons will be transferred through this wire. And this wire, the connection between this electrode and this electrode through this wire, is the one that we refer to it as an external circuit. Because an external circuit is the one that will explain how, in which direction will the electrons flow. But it is very important when you come to this picture to remember what we explained in terms of redox. What do we mean by oxidation? What do we mean by reduction? If you look at this diagram, you can see that this diagram indicates that the electrons are moving from this side going to the other side. So what does it exactly mean? It means the zinc electrode will be the one that will lose electrons. And if zinc loses electrons, the electrons move from the side of zinc half cell to the side of copper half cell. But not forgetting that I said metals, as metals, are able to lose electrons. However, metals cannot gain electrons. So it is not going to be fair, or it's not going to be correct for me to say the zinc electrode will lose electrons and be gained by copper. I will not say zinc electrons are gained by copper. Remember, copper is also a metal. So it means copper cannot gain those electrons, but copper can make those electrons to be transferred to its electrolyte. So as we go into details with what is exactly happening in the two half cells, then that we can understand exactly what is going on. Now, on the zinc plate, that's where the electrons are lost. The electrons are lost by zinc as a metal, because a metal can be able to lose electrons. But what makes zinc to lose electrons? The zinc as is connected to the copper, the zinc half cell and as is connected to the copper half cell. What makes the two to transfer electrons is because of the difference in potential difference. I think we know that, we understand that electricity can flow if there's a potential difference between two substances. So the potential difference between zinc and copper is the one that will make the electrons to be transferred, is the one that will make zinc to lose electrons and undergo oxidation reaction. And immediately when zinc loses electrons and it undergoes oxidation, it means zinc electrode is an anode, because anode is where oxidation occurs. And then copper is the electrode whereby reduction will occur. And because copper is the electrode that where reduction will occur, we refer copper as the cathode in that specific half reaction, this one. So here, copper is our cathode and zinc is our anode. Please, learners, do not confuse the electrodes and the agents, because the electrodes are the metals that are responsible in those half cells in terms of electron transfer, in terms of the other one losing electrons and the other one making sure that those electrons are transferred to the other side. So in terms of the electrodes are not like agents. In this example, zinc is the one that loses electrons, but copper is not the one that will gain those electrons. Copper will make it possible that those electrons are transferred so that they are able to be gained. So what will happen to the zinc electrode or to the zinc half cell? When reaction or when the cells start to function, I'm going to explain the two half cells, what is exactly happening inside those two half cells immediately when the zinc, because the half cells, remember, we did them last year in grade 11, but maybe we never go into details in terms of explaining what is exactly happening inside them. When we have a zinc half cell, use my hand, and then we have a zinc electrode, which is immense inside the zinc half cell. Let's say we have zinc sulfate. Our electrolyte is zinc sulfate. Ne? Is ZnSO4. So we know that if it is zinc sulfate, it means we have ions of zinc and ions of sulfate inside the zinc sulfate solution. So let's say this is a neutral zinc electrolyte. Therefore, it means, what do we have? I will separate the ions. Let's say we have Z2N plus and SO4 2 minus. Another maybe Z2N plus and SO4 2 minus. Now, when the cells start to function, immediately when the zinc starts to lose electrons, immediately when the electrons of zinc are being lost on the side of the zinc electrode, what is going to happen is, when zinc loses electrons, the zinc ions, some of the zinc ions will erode and come to the electrolyte of zinc. Meaning that the loss of electrons makes the zinc to have more positive, because we know that if an atom loses electrons, it becomes a positive ion. And it means now there will be more positive ions forming on the side of the zinc electrode. And those ions will go into the solution of the electrolyte of zinc. And when you look at the electrolyte, now you can see now that the number of negatives and the number of positives are no longer balanced, meaning that there are more positive ions in this electrolyte as compared to the negative ions, because the zinc will erode and positive ions of zinc will come into the solution. And immediately when it is like this, we say the zinc electrode becomes a negative electrode. What makes it to be a negative electrode? Because of the transfer of those electrons. The zinc electrode is not connected to anything. It becomes negative electrode because of the formation, because of the loss of electrons towards the side of copper. So a zinc electrode will become a negative electrode. That is why when you look at the previous diagram, you can see that the zinc electrode, it becomes negative. And immediately when the zinc electrode becomes negative, is because of the loss of electron on the side of zinc towards the side of copper. So it is very important to say zinc becomes a negative electrode after losing the electrons towards the side of copper. And what will happen to the electrolyte will now start to become more positive. And immediately when the electrolyte becomes more positive, it means now there is no stability anymore in this half cells and in this galvanic cell. Therefore, something must be done. Something must be done so that it can go back to normal. Because immediately when there's an imbalance in terms of the ions, therefore the cell cannot function well. But what will happen? Immediately when the zinc erodes and loses electrons, the mass of zinc decreases. So the mass of zinc will start to decrease. Now, in terms of the half cell, we are not going to concentrate too much on these sulfate ions, because when you look at the sulfate ions, nothing is happening on the sulfate ions. Actually, they act as a spectator. They are just there inside that solution as spectator ions so that they balance everything. But what is happening is the zinc that will change and become zinc 2 plus. So when you write the half cell or the half reaction of zinc, it's going to be zinc, which is a solid, going to what? Changing. After losing electrons, zinc will become Zn2 plus, which is no longer a solid but is now an aqueous plus. How many electrons have zinc lost? 2 electrons. So this is a half cell of zinc showing that zinc has lost. So when you look at the oxidation number of zinc, zinc is 0. All atoms have oxidation number of 0. But immediately when it loses electrons, it becomes 2 plus. So what happens to the oxidation number is from 0 to 2, showing that there is an increase in the oxidation number. Therefore, by this increase in the oxidation number is an indication that zinc has undergone oxidation reaction, because the increase in oxidation number indicates oxidation reaction. Therefore, immediately when this zinc undergo oxidation reaction and the mass of zinc decreases, therefore what will happen to the copper side? When you look at the copper side, just like the zinc side, is having copper sulfate solution where there are copper ions and there are sulfate ions. I'll just write 2,2. Then we have copper. This is a... Now, from our example, you can see that the color that we gave copper was blue in color. And one, you can ask yourself, why is copper? They are both sulfate compounds. They are both sulfate electrolytes. But when you look at copper sulfate is blue in color. Then it means there is something that is, there is a specific ion that is responsible for this blue color of copper. When you look at both of them, they both have sulfate ions, but there is zinc this side, there is copper this side. So this zinc side is a clear color. It means zinc and sulfate didn't change any color, but there's still a sulfate and a copper, but there is a blue color. So you can ask yourself, what makes the solution now to be blue? So what makes the solution to be blue is not the sulfate ion, because the sulfate ion is common in both the electrolytes, but what makes the solution to be blue is the copper 2 plus ion, not copper ion, but copper 2 plus ion, because we still have other copper ions that are not 2 plus. So the blue color is because of the copper 2 plus ion being present in the solution. So what will happen here is that the electrons definitely will come from the side of zinc. Remember, there was zinc this side. So I just want to concentrate on the side of copper only so that we know exactly what is happening inside the copper half cell. So the copper will be able to transfer those electrons up to the bottom of the electrolyte. Then inside the electrolyte, there are sulfate ions, which is SO4 2 minus. There are Cu2 plus ion, which is Cu2 plus. There are positive and negative ions, cation ions and anions. So what will happen when the electrons are coming to the bottom of the copper electrode? The copper electrode will not be able to gain those electrons, but the copper electrode will just make it possible for electrons to be in the contact with the electrolyte. According to the law of charges, like charges attract, unlike charges repel. So immediately when there are electrons which are negatively charged on the copper electrode, therefore the positive copper 2 plus ions will be attracted towards the copper electrodes and will go back to copper and will form copper atom. Meaning that what will gain those electrons? The electrons will be gained by the copper 2 plus inside the electrolyte, which was made possible by copper to transfer those electrons, and the SO4, the SO4 2 plus will remain as it is, as we have seen also on the zinc side. The sulfate ions didn't do anything. So it means now the copper 2 plus will gain those electrons, and when they gain those electrons, they will become N copper. Why copper 2 plus gain? Remember, for the copper 2 plus to go back to their normal states, they must be able to gain, because immediately when they are copper 2 plus, it means they have already lost electrons. So for them to go back to copper, they must gain electrons. So in terms of the half cell, it means the copper 2 plus are going to gain the 2 electrons, which they lost some time, and they are going to go back to copper. So copper 2 plus is an aqueous, and copper is a solid. So copper 2 plus are going to gain those electrons. Now, you can ask yourself, what gained? Which substance has gained electrons? Is it copper or is it copper 2 plus? According to this half cell, what gains electrons is copper 2 plus and not copper. So in terms of the agents, we have seen that zinc solid has undergone oxidation and gave you zinc 2 plus, which is an aqueous, plus 2 electrons. So in terms of the agents, when we compare the two half cells, we can see that, okay, we know that this is oxidation reaction and the other one is reduction reaction. Why reduction? Here we have the side of the reactants and the side of the product. Also here, there's the side of the reactants and the side of the product. So what is happening is that on the zinc half cell where the oxidation has occurred, what has been formed is the copper 2 plus. So what has increased? The number of the product ions has increased in the zinc half cell, and the number of the reactant ions, because this is the reactant side, this is the reactant side, this is the product side, this is the product side. What do we mean by reactants? Reactants are something that can come together, undergo chemical reaction, and give you a product. So we always start with the reactants and end with the product, because this is a one-direction reaction, it's not reversible, meaning that a copper 2 plus has gained electrons and became copper, but here a zinc has lost electrons and becomes zinc 2 plus. So the copper 2 plus are the reactants ions, and the zinc 2 plus are the product ions, are the ions that were formed as a product, but these ones are the ions that reacted. So there's a confusion sometimes to say, what do you mean by reactant ions? What do you mean by product ion? Reactant ion, it means that ion reacted to give you a product. And then in terms of the product ion, it means that specific ion was formed as a product. So therefore, because of these abnormalities, the zinc, we have seen from the half cells that the zinc side is becoming more positive and the copper side is becoming more negative. Why is the copper side becoming more negative? Immediately when the copper ions are moving from the solution towards the copper and forming more of this copper, the copper itself will increase in terms of the mass because there will be more of the copper forming. But the zinc will decrease in the mass because more of the zinc ions are going towards the solution and making the mass of zinc to decrease. And because of that, the solution which is blue in color, will start to fade. Why the solution is fading? Because now the copper ions are moving away. They are changing from being copper ions, which are responsible for the blue color, towards the copper, which is, and they are not going to be found now as many as they were inside the solution. But what will be more now is the negative. Therefore, the salt bridge. The salt bridge will see this abnormality between the two half cells and say, okay, let's say this is the zinc and this is the copper. So this is zinc and copper. And this is the salt bridge. And they are connected by, let's say, a voltmeter. And this is the external circuit, and then we will refer to this salt bridge as the internal circuit. So, because we have seen that the zinc side is more positive and the copper side is more, let me just write more, the electrolyte is more negative. Therefore, the salt bridge, remember, a salt is always also made with a positive and a negative ion. So what will happen? If, let's say, we use a salt bridge, which is potassium nitrate, KNO3. Potassium nitrate has a potassium ions with a nitrate ions. So there are positive ions and negative ions. So what will happen? The salt bridge will try and balance the two half cells by doing what? By releasing the ions. The one which is more positive will try to balance the side which is more negative. And the one which is more negative will try to balance the side which is more positive. So the salt bridge, the function of the salt bridge is to try and bring back the balance between the two half cells so that there is no one that is more positive and there's no one that is more negative, so that the cell can function well under standard conditions. So that is the main focus of the salt bridge. Okay? This is the explanation that I was doing in terms of the movement of ions between the salt bridge and the ions. And here also it explains the movement of the ions. So these are the functions of the salt bridge: to complete the circuit, to make sure that the two half cells do not mix, and to maintain the cell neutrality so that at least the cell can be able to function very well. So that is the main thing that the learners must understand in terms of the electron transfer. The electrons will always transfer from the oxidation side to the reduction side. And the cations, the positive ions, will go to the reduction side where the cell is now starting to be more negative. And the anions will go to the oxidation side where now the electrolyte is starting to be more negative, and try to balance the two. Then, as this cell is occurring like that, as this reaction is occurring between the reduction and oxidation, it means now the current will start to form. And immediately when you start connecting these two half cells, you will always have a maximum voltage of that specific, or the maximum potential difference of that the entire cell. And as the cell is starting to function, you will see that the voltage of the cell is decreasing. So what makes the cell to decrease? Remember, the concentration of the reactants, and now they're starting to decrease in terms of the concentration of the reactants and the concentration of the product. So the V cell will start to decrease. And the V cell will decrease up to the point where the V cell is 0. When you see that your V cell is 0, it's not that the reaction has stopped. It means now the rate of the reduction reaction is equal to the rate of the oxidation reaction, as we did the chemical equilibrium. Chemical equilibrium means the forward reaction is equal, the rate of the forward reaction is equal to the rate of the reverse reaction. Now, the redox reaction is occurring in a same rate. Now, the 0 means, so the voltmeter reading will read 0. When the voltmeter reading reads 0, it means now the cell reaction is now reached equilibrium. And if it has reached equilibrium, in our layman's tongue, we normally say the battery is flat. When we say the battery is flat, actually we don't mean the battery is flat. We mean that the cell has reached equilibrium. So we normally say that, okay, you must recharge your battery. You must recharge it. When you recharge, there are some rechargeable batteries, of course. So when you recharge it, it means there's something that you must do with the two electrolytes so that they can give you the desired product. So what must you do? In terms of the two half cell, how can you make sure that you go back to your... Remember, the electrolytes that was mostly used in this reaction was the one that of copper sulfate, whereby the copper ions were used in terms of forming the copper atom. So you need to increase the concentration of the of one of them. You cannot increase the concentration of the zinc ions, because if you increase the concentration of the zinc ions, it means there will be more of the positive ions which are not needed, but you rather increase the concentration of the copper sulfate ions, the ones that will be able to use. So the cell will decrease as the concentration of the product ions increases and the concentration of the reactants ions decreases until the equilibrium is reached. So the product of the product ions and the concentration of the reactants ions is what I was trying to explain in the previous slide, to say, what do you mean by the product ions? We know that the product ions are the zinc ions in this specific cell, and the reactant ion are the copper ions in that. And then when it reaches equilibrium, then the V cell will read 0. Okay? Now, we have a potential, when we write half cells, we have what we call the standard reduction potential table. The standard reduction potential table will be given to you learners so that you know how to write the half cell. All the half cells on the standard reduction potential table are written as reduction. So for you to be able to write oxidation, it means you must write the opposite. Meaning that if you look at the copper half cell, this is an example of the copper half cell. Okay, let me use this one, which is the one that I was using in my reaction. Copper 2 plus 2 copper giving you. So if copper undergo reduction reaction, you will write it exactly as it appears on the reduction potential table. However, if it undergo oxidation reaction, it means you must write it vice versa. And what is important is that all of them are also written as equilibrium. So when you write the oxidation half reaction, you must remove the double arrows and put a single arrow that is going forward. Because when you look at, let me take an example of copper and iron half cell. If you look at iron half cell, it is written as Fe 3 plus 3 electrons, giving you it's like this on the half cell Fe, and copper is written as Cu2 plus 2 electrons, and then going to Cu. Now, the first thing for you to be able to write the two half cell, you must identify which one between the iron and copper undergo oxidation. So what will make you to understand that? The reduction potential table, unfortunately we have just a snapshot of the reduction potential table on our screen. But on the sides, when you have the reduction potential table, it will tell you in terms of the increasing in oxidizing ability and the increasing in the reducing ability. So when you look at this one, when you go down, the numbers become more positive. When you go up, the numbers become more negative. So the ones that are more negative as compared to the other ones are the ones that will normally undergo oxidation, and the ones that are more positive are the ones that will undergo more negative, because we have the EMF values that will indicate what is the voltage of that specific half cell. Now, if you look at iron and copper, you can see that the value of iron is negative 0.06 volts, and copper is positive 0.34 volts. So from the two values, you can immediately determine which one will undergo oxidation and which one will undergo reduction. So from this one, you can see that copper, because of being more positive, will undergo reduction, and iron, because of being more negative, will undergo reduction. Even if the numbers are all positive or all negative, when they are all positive, the one with the smallest number is the one that will undergo oxidation, and the one with the bigger number will undergo reduction. But when they are both negative, obviously the one with the big negative, like for example, when you look at negative 0.13, let me just remove this so that we can understand what we mean by more negative. Negative 0.13 as you compare to it with negative 0.27. When you compare 0.13 and 0.27, you can see that 0.13 will be bigger than 0.27, meaning that if these are the potential values of two half cells, it means this one will undergo oxidation and this one will undergo reduction, because the bigger the negative number, the smaller the number is. The bigger the positive number, the bigger the number is. That is the difference between positive and negative, understanding it from the mathematics perspective. Now, when you look at the example that I just gave of copper and zinc, of copper and iron, you can see that now iron and copper they are losing in a different way. Iron, it was so we have identified that ion will undergo oxidation. So it means it's going to be Fe, which is a solid, going to Fe 3 plus 3 electrons. Therefore, the copper, it means it will undergo reduction, which is aqueous, plus 2 electrons going to Cu, which is a solid. So, from this reaction, you can also be able to say which one undergo oxidation, which one undergo reduction. And you can also see which one is a reducing agent, which one is an oxidizing agent. For the method that this zinc, the ion loses electron, it means it undergo oxidation, and copper undergo reduction. But it is not that always copper undergo reduction. There are some instances whereby copper can also undergo oxidation. It depends on what is that copper reacting with at that specific instant. Now, when you can see these two half reactions, we can be able to write the net reaction from this. So how do we write the net reaction? The net reaction, we are going to write it by making sure that the number of electrons given by the ion and accepted by copper are equal. So how do we do that? We have 2 electrons released by ion. We have 2 electrons gained by copper. So for you to write the net reaction, you take the number of electrons that are transferred, that are released by ion, and multiply on the reaction of copper. So it means it's going to be multiplied by 3, and here we are going to multiply by 2. When we multiply everything by 2 here, and when we multiply everything by 3 here, it means the number of electrons gained and the number of electrons lost, they are going to be the same. Now, what we're going to have, you're going to have 2 Fe solid, giving you Fe 3 plus, because it's multiplied, it's 2 Fe 3 plus, 2 multiplied by 3 is 6 electrons. Therefore, the other one is going to be 3 Cu solid, Cu2 plus aqueous, plus 6 electrons, giving you 2 Cu solid. Now, immediately when the number of electrons are now equal, we are going to add the 2, because it's a net. Net means add the 2 reactions. We are going to add, and when we add, the number of electrons will cancel one another, because the other one is on that other side of the arrow, as we treat the arrow as an equal sign, and the other one is on this side of the arrow. Immediately when we cancel this, so when we write the net cell reaction, the net cell reaction is going to be, we're going to have whatever that is on this side of the arrow, we are going to write this side of the arrow, and whatever is on that other side of the arrow, we're going to write it on that. So it's going to be 2 Fe, which is a solid, plus 3 copper 2 plus, which is an aqueous, going to 2 Fe 3 plus, plus 2 Cu, what is it, 2 C3, even here it was 3 Cu solid. So it means now this reaction is balanced. This is a balanced net cell reaction. Then from the balanced net cell reaction, you can also be able to write the overall cell reaction. By the overall cell reaction, now you indicate what exactly happened in terms of the galvanic cell, all the components that were present in that galvanic cell. So you will also indicate the salt bridge. But now, how do we write it? When you write in a cell notation, because a cell notation is not the same as the net cell reaction. A cell notation under standard condition, the standard condition we also explained last year, whereby we said the temperature is 25 degrees Celsius and the concentration is 1 mole per decimeter cube. And in terms of the gases, the pressure is 101.3 kilopascals. So the standard conditions are the ones that we are going to use in terms of our operation of a galvanic cell. So our cell, the previous cell, as we're gonna take it like the way we did it, it was 2 Fe, which it was a solid, plus 3 Cu2 plus, giving you 2 Fe 3 plus, plus 2 3 Cu, which is a solid. So when we write the cell notation now, we're gonna say from the ion to the ion 3 plus ion is our oxidation side, separated by the salt bridge, and then we write, so it's gonna be A, B, C. We can say A, B, C. The anode side, salt bridge, and the cathode side. Meaning that we're going to write the anode side and then put the salt bridge and write the cathode side. So when we write the anode side, we know it started by being an ion, which was a solid, and then we say slash. This slash, what does it do? It's a phase boundary. It separates the two phases, phase boundary. It says this is a solid and then this is an aqueous. So we use a phase boundary. We use one slash. Then for the salt bridge, we use two slash. And then it's going to be, now, this side it was ion to ion 3 plus. So for the copper one, it's from copper 2 plus to copper. So it's going to be Cu 2 plus, which is an aqueous, slash Cu, which is a solid. So when you read it, you can see that from this cell notation now, is the cell notation, it is showing you exactly what was happening in this galvanic cell, all the components that were forming the galvanic cell. So it was an ion solid undergoing oxidation reaction, losing electrons, and forming ions. And then the salt bridge was separating the two half cells, and then we have copper ions giving you copper. Now we can also use this, the same, this is just explaining, these are the standard conditions. This is what I was trying to refer, but this one is the cell notation showing the salt bridge. But there are some instances whereby now the faces of these compounds that are reacting are the same. In that instant, we don't use the slash line, but we use a comma. Let's say we have an aqueous and another aqueous. When you have an aqueous and you go to another aqueous solution, you cannot use a slash because the slash is only used for a phase boundary, as faces are different. But if the faces are the same, it's just that I don't have an example that I can give right now to show where the faces are the same, where we use a comma, not a slash. So this is a cell notation for the zinc copper half cell that we have used in the previous example. Then we can also use this okay, this was just a cell notation again. We can also use the half cells to calculate the EMF of the cell so that we know how much electricity can we form from this specific cell, depending, of course, on the potential difference of the cell. So when we use that, we use what we call the EMF of the cell. So for you to calculate the EMF of the cell, you must be firstly identify the cathode and the anode. You must also be able to say which one undergo oxidation, which one undergo reduction. And then you are going to use the cell reduction potential table so that you get the values of each half cell. And the values of each half cell will assist you to know how much is this half cell. So this is an example of the zinc copper half cell, whereby we have zinc and copper. We know that zinc undergo oxidation and copper undergo reduction. The formula to calculate the EMF is provided to you on your data sheet. So you copy it exactly as it appears on the data sheet without leaving anything from what you have seen on the data sheet. Then the formula say is going to be E reduction, well, EMF is equal to E reduction minus E oxidation, or E cathode minus E anode. So the theta that is written on top of that E cell is very important. It must be part of your formula because for each and every formula we get a mark. Therefore, because copper, when you look at the table, it was 0.34. You substitute 0.34 and then minus, because this minus is always there because it's part of the formula. And then zinc, if you're going to look at your table, the potential reduction potential table, you will see that the value of zinc potential is minus 0.76 volts. And then for this, you are going to get positive 1.10 volts. And this positive sign indicates that this reaction occurred as a spontaneous reaction. And as a spontaneous reaction, it means it's a galvanic cell. Therefore, it is very important to understand that. So these are the conditions that I was explaining in terms of the standard conditions to say on which conditions can we expect this is when we have that temperature and that pressure of 1.3 kilopascals and that temperature. Now, we know that the values on the standard potential table were all received because of the hydrogen electrode. The hydrogen electrode, when you look at it from the potential reduction table, is 0.0. So all the values that were written on that potential table were referred from the hydrogen, because anything added to 0 or anything subtracted from 0 is that thing. So hydrogen is going to be used as a standard electrode. And when you write the half reaction, you must know that hydrogen will also be written as any other half reaction. So you must not be confused by when you see a hydrogen half cell and think that hydrogen half cell is going to be treated in a different way. It's just there. Okay, learners, thank you so much and all the best for this year. Thank you.